Today we are looking at K-Pure Math Unit 2, 2022 exam. Let us not waste any time and we'll begin right away. So question 1, using the Marvel's theorem, prove that sine 5 theta over sine theta is equal to 5 minus 20 sine square theta plus 16 sine to the power of 4 theta. So using the Marvel's theorem, we can write cos 5 theta plus I sine 5 theta as cos theta plus I sine theta raised to the 5th power. So remember, the Marvel's theorem states that if you have a complex number in its polar form and they raise it to whatever power, to the n power, and in this case the 5th power, we can just simply multiply the angles by whatever the power is. In this case it's 5. Right, so we're going to do the expansion, and to get the coefficients of this binomial expansion we can use Pascal's triangle or we can use combination. Let's use combination. So the first coefficient will be 5 choose 0. So let's begin the expansion. So the first term cos, we raise it to the 5th power there, and the second term I sine theta, raise it to the power 0. Next coefficient is 5 choose 1. So the cos theta, as we go along, the cos theta, the power in cos would decrease and the power in sine would increase. So the next term will be cos theta raised to the 4th power and I sine theta raised to the 1st power. Next coefficient is 5 choose 2. So we raise cos theta to the 3rd power, so it's falling, and I sine theta, the power is increasing, so I sine theta square. Next term, next coefficient will be 5 choose 3. We raise cos theta to the 2nd power and I sine theta to the 3rd power. Next, 5 choose 4, and we raise cos to the 1st power and I sine theta to the 4th power, and the final term, coefficient 5 choose 5, which should be 1, cos theta raised to the power of 0 and I sine theta raised to the 5th power, I sine theta to the 5th power. Alright, let's simplify. Now remember, we're only interested in finding sine 5 theta, alright, which represents the coefficient of the I. So we can equate coefficients of the I. So we only want the imaginary part on both sides. So on the left hand side, the coefficient of the I is sine 5 theta. And on the right hand side, we're only interested in the terms with I. So the first term here, I sine theta to the power 0. Now notice, when you have a non-zero term to the power 0 here, you'll end up with 1. So the first term would not be a term in I. The second term, yes, there will be a term in I. See, this is I sine theta raised to the power 1, so there will be an I. But we only want the coefficient of the I. So we take out the 5 choose 1, or the value of 5 choose 1. That's 5. And we have cos theta raised to the 4th power. And then we have sine theta. So we're not restating the I. We only want the coefficient. So on the left hand side, notice we only took the coefficient, sine 5 theta. The same for the right hand side, we're only taking the coefficient. Alright? So next term is the third term here. Notice this term here, there will be an I square. Now I square is equal to minus 1. So this third term will not be a term in I. So this third term will not have an I. Alright? The next term, we'll end up with an I cube. We'll end up with an I cube. Alright, now let's look at what I cube is. I cube is equal to I square times I. And remember, I square is minus 1. So I cube is actually minus I. So this term will have a minus I. So it'll be a negative term. And 5 choose 3. The value of 5 choose 3 is 10. And then we have a cos square. Let's erase this. So we have 5 choose 3 is 10, and we have a cos square theta. And of course we have sine cube theta. Next term is this term. Would have I to the power 4. Now remember, I to the power 4 is I square times I square. Alright, I square is negative 1, so it's negative 1 times negative 1, which is 1. So this term will not be a term that has I. And in the final term, we'll have an I to the 5th power. Now the final term, we'll have an I there to the 5th power. Now I to the 5th power is I to the power 4 times I. Now I to the power 4 is 1. So I to the 5th power is actually 1 times I, which is I. So the final term will be a term in I. So it's 5 choose 5, which is 1. Cos theta to the power 0, which is also 1. And then we have sine to the 5th power times I to the 5th power. But I to the 5th power is just I. But we're not restating the I. All we're restating is the coefficients. Now you'll remember we're actually asked to find sine 5 theta divided by sine theta. So let's divide both sides by sine theta. Let's divide both sides by sine theta. So divide both sides by sine theta. So the right hand side, so we divide each term by sine theta, you'll actually end up with 5 cos to the 4th power theta minus 10 cos square theta sine square theta. So we're dividing every term by sine theta. And then divide sine to the 5th power by sine to the 4th power theta. Let's continue. Now, notice what we're asked to show. Very importantly, notice you're asked to prove this. Notice all the terms in the proof are terms in sine. Right? So we only want terms in sine. So we don't want any term in cos theta. Alright? So we're going to let's rewrite now. This is 5. This is cos square theta times cos square theta minus, and then this is, put the 10 on the sine square theta. So this is 10 sine square theta times cos square theta plus sine to the 4th power theta. Now remember, cos square is actually 1 minus sine. So this is 5 into 1 minus sine square theta. So we rewrite cos square theta as 1 minus sine square theta. So cos square times cos square, that's 1 minus sine square theta times itself. So you're left with that, and then the next we have minus 10 sine square theta, and the cos square, we can rewrite cos square as 1 minus sine square theta plus sine to the 4th power. Alright, so now we can expand. So so we have 5 let's expand this bracket. So it's 1 minus sine squared times itself. We end up with 1 minus 2 sine squared theta plus sine to the 4th power. Expand. Next, we have, so minus 10 sine squared theta times each term in the bracket. So we have minus 10 sine squared theta plus, and minus 10 times minus sine, so it'll be plus 10 sine to the 4th power theta plus sine 4th power theta equal to, distribute the 5, so we end up with 5 minus 10 sine squared theta plus 5 sine the 4th power theta, and then we have minus 10 sine squared theta plus 10 sine to the 4th power theta plus sine to the 4th power theta. So we can group the like terms, so the only constant there is 5. Terms in sine square, now we have minus 10 sine square, and then minus 10 sine square, that's minus 20 sine square. And then the terms in sine to the power 4, so we have 5 plus 10 plus another 1, that's 16 terms where you have sine to the 4th power theta. Alright? So 5 minus 20 sine squared theta plus 16 sine to the power 4 theta. Notice that's exactly what we're asked to prove. 5 minus 20 sine squared theta plus 16 sine to the 4th power theta. I just did that. Right, let's get into question 1b. Given that 3 plus 5i is a root of the quadratic equation z squared plus pz plus q equals 0, determine the values of p and q. So we know one of the root is z equal 3 plus 5i. So we know the other root will be the conjugate, which is 3 minus 5i. The conjugate of 3 plus 5i is 3 minus 5i. So if we can just group it, so we have z minus 3 minus 5i equal to 0. Likewise, group everything on one side. We end up with z minus 3 plus 5i is equal to 0, which means that either of these, if we should take the product of z minus 3 minus 5i and the product of z minus 3 plus 5i, since one of these brackets is 0, then this should be r. Alright? So either this bracket is 0 or this is 0, because since one of these is the root, then if we expand these brackets, we should get 0. Now, let's expand the bracket. So we take the z and multiply to each term in the second bracket. The minus 3 do the same thing. The minus 5i will do the same thing. So we take the z and multiply to each term there. So we end up with z squared minus 3z plus 5zi. Take the minus 3, expand to each term in the bracket. So we end up with minus 3z plus 9 minus 15i. And we'll do the same thing with the minus 5i. So minus 5i times z, that's minus 5zi, minus 5i times minus 3, that's 15i, and minus 5i times positive 5i, that's minus 25 I square. Equate that to 0. So let's group like terms now. So we have z square. We have z square, and we have minus 3z. We have minus 3z minus 3z. That's minus 6z. Here we have 5zi, cancel with negative 5zi. We have negative 15i, cancel with 15i. And we have minus 25i squared. Now remember, the value of I squared is minus 1. I squared is equal to minus 1. So that's minus 25 times minus 1. That's positive 25. So if we equate the coefficients here, look at p. P is the coefficient of the z, which is negative 6. The constant there is q, which is 25. So p is minus 6. And q is a constant, 25. Next. A complex number z is such that the argument of z minus 2 is equal to pi over 2, the equivalent of 90 degrees. And the argument of z is equal to pi over 3, the equivalent of 60 degrees. Determine the complex number z. Now, for the first one, let me do this first one first. The argument of z equal to pi over 3. So the argument of z is equal to pi over 3. Now we can replace z. We can replace z with x plus iy. So the argument of x plus iy is equal to pi over 3. Now how do we find the argument of a complex number again? So it's tan inverse. Argument is tan inverse the imaginary over the real. So it's tan inverse y over x is equal to pi over 3, which means that y over x is equal to tan pi over 3. So y over x, tan pi over 3, that's root 3. And if we times both sides by x, y is equal to root 3x. Let's look at the other one. The argument of z minus 2 is equal to pi over 2, or 90 degrees. And again, replace z with x plus iy. So it's x plus iy minus 2 is equal to pi over 2. Let's put the real parts together. So the argument, let's put the real parts together. The real part would be x minus 2 plus iy equal to pi over 2. And again, the argument is tan inverse, let's separate that. Tan inverse the real, the imaginary over the real. So tan inverse y over x minus 2 is equal to pi over 2. Which means that y over x minus 2 is equal to tan pi over 2 which means that y over x minus 2 is now tan pi over 2, that's undefined. Tan pi over 2 is undefined. Alright, I tried that on a calculator, end up with math error, which means that for y over x minus 2 to be undefined, it means that the x minus 2, this denominator would have to be 0. So x minus 2 would have to be 0, because y divided by 0 is undefined, so which means that x would have to be 2. Notice when x is 2, the denominator there is 0, which would make it undefined. So x equal to 2, and y is equal to root 3x. So therefore, if I plug this into this, replace x with 2, y would be equal to root 3 times 2, or we say 2 root 3. So therefore the complex number z, remember z is x plus iy, the x is 2 and the y is 2 root 3. So z is x is 2, sorry, plus 2 root 3 I. Let's move on. Given that x squared plus y squared all square equal ax squared y, use implicit differentiation to find dy by dx. So to differentiate, of course we can use chain rule, or we can just first expand. Let's expand x squared plus y squared. So x squared plus y squared times itself, we get x to the 4th power plus 2x squared y squared plus y to the 4th power equal ax squared y. And now we can differentiate implicitly. Differentiate x to the power 4, that's 4x cubed. Differentiate 2x squared y. I'll apply the product rule. So differentiate 2x squared, I get 4x. I'll leave the y squared alone. Plus alternate now. So I'm going to keep the 2x squared. Differentiate y squared, we'll get 2y times dy by dx. Differentiate y to the power of 4, we'll get 4y cubed dy by dx. Over the right hand side, again we're using product rule. Differentiate ax squared, we'll get 2ax, leave the y alone, plus I'm going to keep the ax squared this time. Differentiate y, I get dy over dx. And then now we're going to group all the terms with dy by dx. So let's group all the terms with dy by dx now. So here we have a dy by dx. So this term here, the third term on the left hand side, that's what? That's 4x squared y. Dy by dx. What else have dy by dx? The 4y cubed. So 4y cubed dy over dx. And then and we group this term over here, ax squared. So it's now minus ax squared dy over dx. We group everything else on the other side. So we have 2axy. We have minus 4x cubed. And we have minus 4xy squared. So now we are going to factor out the dy by dx. So we factor out the dy by dx term. So we are left with 4x squared y plus 4y cubed minus ax squared. And on the right, just restate this. So 2axy minus 4x cubed minus 4x y squared. So we divide both sides by the bracket. 4x squared y. So divide both sides by the bracket here. We have this bracket into itself gives us 1. So dy by dx is equal to all that we have here on the right hand side. 2axy minus 4x cubed minus 4xy squared over 4x squared y plus 4y cubed minus ax squared. Let's move on. So now we're at question 2. No, before is a partial fraction question. Now before we look question 2, it's very important to know that the denominator here on the left hand side, x to the 4th power minus 1, we can write it as a difference as squares. So that's x squared minus 1 into x squared plus 1. which we can break down even further. The x squared minus 1, we can rewrite as x minus 1, x plus 1, and the x squared plus 1. So these are all the factors. And notice all of these factors are on the right hand side here. Alright, so we're going to let x to the 4th power over x to the 4 minus 1 is equal to, so this 1, so we don't know it's 1. Let's call it a. So the constant there, a plus b over x minus 1 plus c over x plus 1 plus d over x squared plus 1. So our job is to show that the value of a is 1, the value of b is a quarter, the value of c is also a quarter, and the value of d is a half. Right? But before we can do that, we need to rewrite, we need to make sure all of these have a common denominator. So we have x to the power of 4 over x to the power of 4 minus 1. Alright? Notice now the first term here is a. Write a over 1. We want to ensure that this first term on the right hand side has the same denominator as the left hand side there. And to do that, we can multiply numerator and denominator by x to the power of 4 minus 1. And that's the whole idea of equivalent fractions. Alright? Whatever we do to the denominator, we'll do the same thing to the numerator. Notice if we could cancel x4 minus 1 over itself, it's still a. Plus, this next term, we want to do the same thing. We want to ensure that it has the same denominator, x to the power of 4 minus 1. X to the power of 4 minus 1. So what we currently have is b over x minus 1. Now, to get this to have the same denominator as this, look at the x minus 1. You have to ensure that you multiply now by x plus 1 and x squared plus 1. So if I multiply by x plus 1 and x squared plus 1, I'll have the same denominator. Alright? So I have to do the same thing to the numerator, x plus 1, x squared plus 1. Likewise, the c, notice for the c is c over x plus 1. And for c to have the same denominator, I need to multiply by x minus 1 and x squared plus 1. So I have to multiply by x minus 1 and x squared plus 1. And of course I have to do the same thing to the numerator. X minus 1 and x squared plus 1. And then the final one, d. So notice we have d over x squared plus 1 and now to get this to have the same denominator as everybody else, I need to multiply by x minus 1 into x plus 1. Remember, I have to do the same thing to the numerator. Or you could just say multiply by, notice the difference as squares, so you could just multiply by x squared minus 1, same thing. So notice all our terms have the same denominator, so we can multiply both sides by, if we multiply both sides, I multiply each term on both sides by x to the power of 4 minus 1. Then what would happen is that we're only left with the numerators. So on the left hand side, I'll only have x to the power of 4. On the right hand side, I'll only have a into x to the power of 4 minus 1 plus, I'll be just left with just the numerators. Because notice all the denominators are representations of x to the power of 4 minus 1. So I will just left with just the numerators. Right? So I will left with b into x plus 1, x squared plus 1, plus c into x minus 1, x squared plus 1 plus d into, and notice what this is. This is really x squared minus 1, right? So d into x squared minus 1. Alright, now we can, to solve, we can let x be equal to different values. So we can say let x be equal to 1, let x be equal to 1. If x is equal to 1, on the left hand side, 1 to the power of 4 is 1. On the right hand side, this would be 0. This would, all the terms would be 0 except the second term here with b. The second term here with b, I would end up with 4b. If x is 1, this bracket will be 1 plus 1, which is 2. And this bracket will be 1 plus 1, which is 2. 2 times 2, 4. That's how I get the 4b. Alright, so divide both sides by 4. B is a quarter. Next, we can let x be what now? Negative 1, so we can let x be negative 1. Alright, so negative 1 to the power of 4. 4 is an even power there, so we'll get 1. Alright, and the other side, if x is negative 1, then this would be 1 minus 1, which is 0. The second term would also come to 0 because negative 1 plus 1, 0. Alright, the final term would have negative 1 square, 1 minus 1, 0. So we'll only be left with the C term in C. So if x is minus 1, the first bracket will be minus 1, which will be minus 2. And the second bracket will be minus 1 square, which is 1. 1 plus 1, 2. So the first bracket will be minus 1, the other one will be 2. Minus 2 times 2. That's minus 4. So it's minus 4c. Divide both sides by minus 4. So c is negative a quarter. Next, I don't think there are any other values we can use to cancel all the brackets. So what we can do is maybe use just a small number as possible. So we can let x be 0. Let x be 0. Now if x is 0, on the left hand side you'll have 0. If x is 0, you'll have in the first bracket 0 minus 1, which is minus 1, so we'll have minus a. If x is 0, here you'll have for the b term, you'll have 1 times 1, because the first bracket will be 1, 0 plus 1, next bracket is 0 plus 1. So 1 times 1, 1, so it's just b. And for the c term, if x is 0, it will be actually minus 1 times 1, which is minus 1c. And for the final, the d term, if x is 0, you have 0 minus 1, so that's minus d. Now remember, we know the values of b and c. So we have 0 equal minus a. The value of b is a quarter, so plus a quarter. The value of c is minus a quarter, so minus c is again positive quarter. Minus d. Alright, so we'll end up with now, let me just put the a and the d on the left hand side. So we'll end up with a plus d is equal to quarter and quarter. That's a half. So a plus d is a half. Alright, that's one equation. Next, what other small value we can use for x now? 2. Next, we can let x be 2. So we can let x be equal to 2. If x is 2, we'll have 2 to the power of 4, which is 16, equal to, if x is 2, again you'll have 2 to the power of 4, which is 16, 16 minus 1, 15, so 15a. For the term in b, if x is 2, the first bracket will be 2 plus 1, 3. The other bracket will be 2 square plus 1, which is 5. 2 square plus 1 is 5. So 3 times 5, 15. So you end up with 15b. For determine C, if x is 2, what you'll have is 2 minus 1, which is 1, and then 1 times, and then 2 square plus 1, which is 5. So 1 times 5, so you end up with 5c. If x is d, what you'll have is 2 square, which is 4. 4 minus 1, 3. So you'll end up with 3d. So let's just group the a's and the d's now. Let's group. Now we know that the value for what we have now. So we have the value of b and c. So 16 equals 15a plus, now the value of b is a quarter. So 15 times b is 15 times a quarter, which is 15 quarters, right? And the value of c is negative a quarter. So 5 of that is negative 5 quarters plus 3d. Let's continue. So if I do some grouping now, I'll have 16, and then let me put the 15a, my bad, so it's 15a. So it's 15a, right? So I'll have 15a plus 3d, and the well, 15 over 4 minus 5 over 4, that's what, 10, positive 10 quarters. And we can subtract 10 quarters from both sides. So we end up with, end up with 16. So 16 minus 10 over 4. You can use a calculator for that. That's 27 over 2. So 27 over 2 equal 15a plus 3d. That's another pair of equations. And we can now solve, right? So from the first one, from the first equation, d, notice d is equal to half minus a. And we can substitute this into this, right? Let's call this equation 1. Let's call this equation 2. So we can substitute d equal half minus a into equation 2. So d equal, from here, d equal half minus a. So we sub it into equation 2. So we end up with 27 over 2 equal 15a plus 3d. But remember the value of, remember d, we're going to replace d with half minus a. So we end up with 27 over 2 equal 15a. Distribute the 3 now, so we get 3 halves minus 3a. So what can we do next now? We can group the a's. So let's do some grouping. So we have 27 over 2 minus 3 over 2 is equal to 15a minus 3 over a. So I end up with, now what's 27 over 2 minus 3 over 2? That's 24 over 2, which is 12, and 15a minus 3a, that's 12a. Divide both sides by 12, a is equal to 1. Alright, so let's test it now. So a is equal, now if a is equal to 1, recall that d equal half minus a. So d equal to half minus a from here. So d would be half minus 1. So d is actually negative a half. Alright, so we have all our values. So we have our value, the value of a is 1. B is quarter, c is negative a quarter, d is negative a half. So let's check the proof. Notice, so we just found a to be 1. Let me just rub out the value of, put them in. We just found a to be 1. We just found b to be a quarter, and c to be negative a quarter, and d to be negative a half. So we've just concluded the proof. So this is quite easily done. Alright, so a is 1, b quarter, c negative a quarter, d negative a half. Part B, or part 2, hence or otherwise determine the integral of that expression there. Remember, we just rewrote this expression. We just rewrote this to be, what was it again? 1. So a plus a quarter, x minus 1, minus a quarter, x plus 1, and then d was minus a half, right? Minus a half, x squared plus 1. So we just rewrote that expression here, this expression here, to be this. Alright, so we simply just rewrite it and integrate it piece by piece. So, gone too far. So let's integrate. So we can use integration by recognition. Integrate 1, we end up with x. Integrate the next term, that's a quarter by recognition, log x minus 1. Next term also by recognition, that's a quarter, right? A quarter minus a quarter, log x plus 1. And the final term, we can use inverse trig function, that's minus a half. And we know we have a constant over a quadratic there, x squared. So the u would be x, a would be 1, so that's just tan inverse. X over 1, that's tan inverse x. Plus c, of course. Next problem seems to be a reduction formula problem. Alright, so let's find in. So in, alright, I'm going to use a formula. I'm going to call this v. Let me call it 1 minus x to the power n v. Let me call v 1 minus x to the power n. And if I find the derivative of v, the derivative of v would be differentiate v, I would get n 1 minus x to the power n minus 1, and then multiply by the derivative of the, so chain rule, I would end up with minus n outside here, applying the chain rule to this, so it's minus n, differentiate negative x is negative 1, right? And let me call the other term u, so let me call u, so let this be that, and let u be equal to e to the ax. So the integral of u will be e to the ax, and we of course a is a constant, treating a is a constant, over a. So the formula I'm using here, so the integral, in be the integral of vu with respect to x. So this is where in would be equal to, the formula I'm using would be v times the integral of u minus, put a large integral sign there, v prime, that's the derivative of v, times, repeat the integral of u. So the integral of u would repeat here also, dx. So I'll just do the substitution now since I have everything. So v is what? V is 1 minus x to the power of n. So v is 1 minus x to the power n. The integral of u would be, here we have integral of u, would be e to the ax over a minus, put a large integral sign there, and this v, and then we put now v prime. Now v prime, we have it here, v prime is minus n. Let me put the n, so it's minus, so minus n, and the double negative, so it will be plus n, and n is a constant. Let me put the n outside here, so plus n outside here, and inside now have 1 minus x to the power of n minus 1, so that's the v prime, times the integral of u, and the integral of u is e to the ax, over a dx. Let me just remove all of this now, avoid confusion. Now, to get it to look like as what we're asked to show, we can do some rewriting here. So let me just put so this a, so right, just for it to look like what we have there up there. So 1 over a, so 1 over a. Now we have 1 minus x to the power n e to the ax plus, so notice this a, I'm going to put this, so plus, I'm going to put this a outside here, since it's a constant, this a, I'm going to put it outside here, so it's n over a times the integral, notice what n over a, so n over a times the integral of 1 minus x to the n minus 1. So only difference between this expression here and what we have down here. Instead of n, we have n minus 1. So this is really I n minus 1. Good? Alright, next, and then so n over a, I n minus 1. Continuing. Hence determine the integral of 1 minus x cubed e to the 2x. Now if you notice, the n here is 3. So we are really being asked to find, let me just write down what I n was again. So I n was equal to, let me just rewrite it. Alright, so I n was equal to this. So this was the original I n. So notice when the 1 minus x is raised to the power of 3, you're being basically asked to find I3. Alright? So let's just come down there. Let's just rewrite everything in the question. Yes, so I just restate the in and the expression that we have for in. But based on what we're asked to find here is 1 minus x to the power of 3. So we're basically being asked to find I3. So I3, and then notice a, e to the 2x, e to the ax. So we're going to use a to be 2. So I3, so n3, a2. So in this expression, I'm going to replace a with 2. So it'll be 1 over 2 1 minus x to the power n, which will be 3, e to the 2x. So simply replacing a with 2, n with 3, plus 3 over 2 I2. 3 minus 1, that's 2. So I need now to find I2. So I'm going to I2. So this time I'm going to replace now the n with 2. So I2 again, a is always 2, right? A is a constant 2. So 1 over 2 e to the 2x. I remember a e to the 2x. And this time now, remember we're replacing n with 2. So this time now, 1 minus x to the n, which is 2. So you find I2. Plus, remember n now is 2, a is 2. So 2 over 2, that's 1. And then n is 2, so 2 minus 1, that's 1. So I subscript 1. But we need I subscript 1. How do we get I subscript 1? So to get I subscript 1, this time we'll come back. This time we're going to replace n with 1. Alright, and a with 2. So again, is 1 over 2. 1 minus x. 1 minus x to the power n, but n is 1. Into e to the ax, but a is 2, right? Plus n is 1, a is 2, so half I subscript 1 minus 1, and that's 0. So let's just find I subscript 0. So remember this was in. So I subscript 0, I get I subscript 0 by replacing the n with 0, right? So I 0 will be equal to 1 minus x to the power of n, which is 0, into e to the 2x. This should be, dx should be here, right? With respect to x, e to the 2x. Remember a is 2, so e to the 2x dx. So remember, so 1 minus x to the power 0, that's just 1. So all we are integrating is e to the 2x. Now integrate e to the 2x is e to the 2x over 2. So I subscript 0 is half e to the 2x. Or we say e to the 2x over 2. Okay, so we know that I0 is e to the 2x over 2. So we can, alright? So we can find now I1. So therefore I1 would be half 1 minus x into e to the 2x plus half times e to the times I0, and I0 is e to the 2x over 2. So which means that I1 is equal to half into 1 minus x e to the 2x plus e to the 2x over 4. Now let's use it now to get I2. Now if you look at this I2, so here's I2, so therefore I2, let's working back up now, so I2 is half e to the 2x. Let me write that's just e to the 2x over 2. So e to the 2x over 2 into 1 minus x squared plus I1. And what is I1? Alright, let me just write it as, let me write this as e to the, let me write it, e to the 2x over 2, this is I1, and let's put the half times the e to the 2x, and then 1 minus x so I2 plus e to the 2x over 4. Let's go over I2 again, just to make sure there is no error. There are no error. So I2, here's I2. I'll just rewrite it. E to the 2x over 2, 1 minus x squared plus I1. And we just found I1 to be, here's I1, e to the 2x over 2. Just put in the exponential term first. E to the 2x over 2 into 1 minus x plus e to the 2x over 4. And now what we really want now is I3. So I3 is all of this plus 3 over 2 times I2. So I3, let's get I3 now. Then just rewrite this. Rewrite this for I3. Half 1 minus x cubed e to the 2x. So I3 half e to the 2x, e to the 2x over 2, 1 minus x cubed. So I3 e to the 2x over 2, 1 minus x cubed, plus 3 over 2 times I2, plus 3 over 2 times the expression we have immediately above here, I2, which is e to the 2x over 2 into 1 minus x squared plus e to the 2x over 2 into 1 minus x plus the final term here, e to the 2x over 4. So 3 over 2 times everything there for I2. Right, can we simplify that? Let's see. Will become now, so what we have here now, so e to the 2x over 2, so e to the 2x over 2, half e to the 2x into 1 minus x cubed plus, let's distribute now this 3 over 2, so 3 over 2 times e to the x over 2, that would be 3e to the 2x over 4 into 1 minus x squared plus, distribute the 3 over 2 to here. Again, we'll have 3e to the 2x over 4 into 1 minus x. And the final term, distribute 3 over 2 to this final term there. We'll get 3e to the 2x over 8. And of course, I'm sure you can factor e to the 2x, but I guess we can just leave it like this. Let's move on. As a matter of fact, let me just factor it. So if so I3, I can rewrite. I'll just say I can factor out e to the 2x. In the bracket, I'll have 1 minus x cubed over 2, 1 minus x cubed over 2, plus 3 into 1 minus x squared over 4, plus 3 into 1 minus x over 4, plus 3/8. And I'm sure you can go even further to get rid of the denominator and factor out 1/8 or something like that, but that should be enough. Induction to prove that, and we have an expression there. So we now begin at 1. So when n is 1, but wait, notice when n is 1, this thing is undefined. Remember the formula for on the left gave us what we call the nth term. So this formula on the left hand side give us what we call the nth term, and the formula on the right hand side give us the sum of first n terms. Sum of first n term. Notice when n is 1, it's undefined. So see, this actually seems to start when n is 2. Alright, this series actually seems to start when n is 2. So I think there's probably an error here. This should be maybe for n greater than or equal to 2. Alright, so we can substitute 2 in the thing here. So the first term is actually when n is equal to 2. So first term is actually when n is 2. And when n is 2, what we'll get is 2 into 2 minus 1 over, in the denominator, 2 squared plus 2 minus 1 all squared. Let's write that out now. So 2 2 is 4, 4 minus 1, 3. In the denominator, 2 minus 1, 1, 1 square 1, 2 square 4. So 3/4. So see, so the first term, the sequence actually begin when n is 2. And the summation for the first term, so the sum of the first term, and the sum of the first term is actually S2. The sum of the first term is actually S2. So we replace, so the summation replace n with 2. So about 1 minus 1 over 2 squared. So it's 1 minus 1/4, which gives us 3/4. Alright, so the formula is true for the first term, and it's not as normally the induction proof we normally start from n is 1, but this is an unusual one. So the sequence begins when n is 2. Alright, so let's continue. So it's true for the first term. So the base step is actually when n is 2. That's the base step. So next we're going to assume true when n is k. And we simply replace everything in the thing there with k. So this will be 3/4 plus 5 over 36 plus that plus 2k minus 1 over k square into k minus 1 all square. And on the right hand side we sum in k terms, so it's 1 minus 1 over k square. Step 3. Now we're going to assume, we're going to show true for n equal to k plus 1. So we're going to add one more term on the left hand side here, and on the right hand side we're summing up k plus 1 terms. So we have 3/4 plus 5 over 36 plus that, and we'll put back in the kth term, 2k minus 1 over k square into k minus 1 all square plus, and we're going to add one more term now. Remember, this is how we're getting the term, so we're going to replace n now with k plus 1 for additional term on the left hand side. So 2 times n become 2 times k plus 1 minus 1 over, and then n square become k plus 1 square in the bracket, k plus 1 minus 1. So in the denominator, n square will become k plus 1 square, and in the bracket replace k with k plus 1. So the bracket, so we just have k square, so we'll end up with just k square here in the second bracket, k plus 1 minus 1, so that's k square, and there we're assuming it's equal to the right hand side. This time we're summing up k terms, so replace on the right hand side, we replace now n with k plus 1. So 1 minus 1 over n square become 1 minus 1 over k plus 1 square. So it become 1 minus 1 over k plus 1 all square. And this step 3 is what we're trying to prove. So we don't know if both left hand side and right hand side are equal. Put a little question mark there. But that's what we're actually trying to prove. So, right, so left hand side, let's try to prove this now. So the left hand side, now notice the left hand side. From 3/4 to the 2k minus 1 numerator there, from 3/4 to this term there. Alright, so by substitution, all of that is equal to 1 minus 1 over k square plus, and here now, what we have now, here 2 into k plus 1 minus 1 over k plus 1 all square times k square. We want to prove that all of this will give us 1 minus 1 over k plus 1 square. Let's continue. Now, one thing we can do is bring everything over a common denominator. So here on the left hand side, so here we have 1. Let's keep this one. Let's keep this one outside, because what we're trying to prove actually is that there's a 1. So let's not trouble that 1 there. Alright, so keep that 1, and then so we have minus 1 over, so we want this 1 over k square to have the same denominator as this. So notice we have 1 over k square. Now to get it to have the same denominator, we can multiply this by k plus 1 square. But of course we have to do the same thing to the numerator, multiply by k plus 1 square for the fraction to remain equivalent. Plus, and again over here, we have what we have now. Same denominator, k plus 1 square times k square. And if we expand the bracket there, we'll get what now? If we expand the bracket, we'll get 2k plus 2 minus 1. Let's continue. Put this equal to 1 plus, let me put this positive term here at the front here. So I'm going to have k plus 1 square, k plus 1 square in the denominator into k squared. That's the common denominator. But I'm going to put the positive terms at the front here. So this will be equal to what? 2k plus 1. So that's 2k plus 1 minus, and then what I have here is k plus 1 square. So minus k plus 1 square. What's k plus 1 square? K plus 1 square is actually k square plus 2k plus 1. Alright, so in the bracket, k plus 1 square. Alright, so we end up with 1 plus, again, the common denominator, k plus 1 all square into k square. If I expand, I have 2k plus 1 minus k square minus 2k minus 1. Continuing, I left with 1 plus the same common denominator, k plus 1 all square, k square. Now 2k cancels negative 2k. Positive 1 cancels negative 1. So all I'm left with is just negative k square. Alright? And of course, now negative k square into itself. So negative k square into itself, given minus 1. So what I can just rewrite this as 1 minus. So 1 plus negative 1 is just 1 minus 1, right? 1 minus 1 over k plus 1 all square. You will notice that's what we're trying to prove. Alright, that's what we're trying to prove in the third step. 1 minus 1 over k plus 1 square. So the left hand side equal the right hand side. So therefore, true for n equal k plus 1. Hence, true for all n, where n, of course, n is greater than or equal to 2. For all n greater than or equal to 2. Let's move on. Hence or otherwise, calculate S30 minus S10. So remember, Sn is a summation. What we have on the form over there, Sn will be, Sn was what now? Sn was, what we have on the right hand side. Let's go back to the original. 1 minus 1 over n square. Sn was 1 minus 1 over n square. So 1 minus 1 over n square. So S30 minus S10 will be S30, replace n with 30. So 1 minus 1 over 30 square minus S10, 1 minus 1 over 20 square. And that should give us what now? This 1 minus 1, that's 0. So we left with just 1 over 20 square minus 1 over 30 square. And that should give us 0.009, something like that. Alright, let's move on. Calculate the sum to infinity of the series 10 over r square minus 1 from r equal to 2 to infinity. I notice r cannot be 1 because if r is 1, the thing is undefined. Alright? So, let's write out some of the terms. And this is definitely not a geometric series. So the formula for sum to infinity that we use, a over 1 minus r, this formula is not applicable because simply is not a GP. Good. So let's try write out some of the terms and see if we can figure out a pattern here. So the first term would be when n is 1. All right. So when n is 1, notice. So this is equal to. So is equal to when r is 2. R starts from 2, right? When r is 2. When r is 2. Before I even get to that, I think the best thing to do is maybe rewrite this thing as partial fraction. So we can use partial fraction. So notice 10 over r square minus 1 is 10 over r minus 1 into r plus 1. So we can do some little rough work there and try to find. So we can write that as a over r minus 1 plus b over r plus 1. So we can try and find the value of a and b, just to rewrite it. So we can let, so this would mean that 10 over r minus 1, let's rewrite it into partial fraction, into r plus 1, is equal to a into r plus 1 plus b into r minus 1. Of course, both of these would have denominator r minus 1, r plus 1, r minus 1, r plus 1. So partial fractions, notice all of them now have the same denominator. Alright, and to get a denominator from r minus 1 to this, we simply multiply top and bottom by r plus 1. To get a denominator of r plus 1 to this, we multiply r minus 1 times numerator and denominator. Right, so of course we can multiply each term by r minus 1, r plus 1. So we'll be left with just 10 equal to a into r plus 1 plus b into r minus 1. And to find the values of a and b, we can let r be equal to 1. If r is equal to 1, what you'll have is 10 equal to a. So a is 5. Divide both sides by 2, a is 5. And we can let r be equal to minus 1. If r is minus 1, what we'll have is 10 equal to minus 2r. Divide both sides by minus 2. Minus 2b, sorry, 2b. We get minus 5. We get minus 5 equal to b. Alright, so in partial fractions, a would be 5, and b would be negative 5. So this series here, we can rewrite it as, we can rewrite this as, so this can be equal to the summation from r equal to infinity, a, and a is 5, and b is negative 5. So replace a with 5, a is 5, minus that. Alright? And of course, to check if this is correct, we can actually put it back together, simplify, and to one common denominator, and the common denominator and the numerator should be 10. Alright, so we'll just use partial fractions to rewrite. So now we can write out some of the terms now, alright? And of course, we're starting from r equal to 2. So when r is 2, what we have is using this, we're going to use this. It's 5 over 2 minus 1. So 5 over 1 minus 5 over 2 plus 1. So 5 over 3. Let's write out a few of them. When r is 3, right, it's better. When r is 3, is 5 over 3 minus 1. So that's 5 over 2 minus 5 over 3 plus 1. That's 5 over 4. Let's do some more. See if we can pick up a pattern. When r is 4, that's 5 over 3. 5 over 4 plus 1, that's 5 over 5. Let's do a few more. About 6 or so. When r is 5, that's 5 over 4 minus 5 over 6. When r is 6, that's 5 over 5 minus 5 over 7. When r is 7, it's 5 over 6 minus 5 over 8. When r is 8, how much of them we need? When r is 8, let's do this last one. When r is 8, it's 5 over 7 minus 5 over 9. That's the one. When r is 9, it's 5 over 8 minus 5 over 10. And so on. Now do we pick up a pattern here? Notice, this term will cancel. Negative 5, 3 will cancel with positive 5, 3. Positive 5, 2 will cancel. No, positive 5, 2 don't cancel with anything. Let's move that. Alright. So this term, so negative 5, 3 cancel with that. Negative 5 over 2 don't cancel with anything. Negative 5, 4 will cancel with positive 5, 4. Negative 5, 5 will cancel with positive 5, 5. See the pattern here? 5, 6, negative 5, 6 cancel positive 5, 6. Negative 5, 7 cancel positive 5, 7. Negative 5, 8 cancel positive 5, 8. And so on. So all the terms in all the brackets will be cancelled except the first two terms. Except the first two brackets. The first term and the first two brackets. The 5 over 1 and the 5 over 2. So this would go on to infinity. Stop and stop, alright? But notice everything would cancel except the 5 over 1 and the 5 over 2. So this is equal to the 5 plus 5 over 2, which is what? 7 over 2, 7.5. Because this is 2.5. 5 and 2.5, that's 7.5. I would say 15 over 2. Let's move on. Determine the Taylor series expansion of sine x, of x sine x over 2 about x equal pi, that's the equivalent of 180 degrees, up to and including the first three non-zero terms. So let's write out the formula for the Taylor series. So f of x equal to, and of course, we're using pi, right? In this case, it would be f of pi plus x minus pi, f of a, but we're using a to be pi, right? So as you putting it right away, f of x minus pi, f prime pi plus, up to determine the first three non-zero terms. Okay, so we stop at x minus pi squared then. First three non-zero terms. So x minus pi square, second derivative of pi over 2 factorial. So I can go up to the second derivative. Let's find the first derivative. So let's find, so f of x, let's find f of pi. F of x is x sine x over 2. So f of pi would be pi sine pi over 2. Now sine pi over 2, that's sine pi over 2, that's 1. So that's just 1 pi, which is pi. Let's find the second derivative, f prime x, and we're going to use the product rule. Alright, so product rule differentiate x, we get 1. So it's 1 times sine x over 2. Plus, this time we're going to keep x now. Differentiate sine x over 2. Or sine half x. Look at it as sine half x. We get half cos x over 2. And then we can substitute pi to get f prime pi. Substitute pi. We get sine pi over 2. Again, sine pi over 2, that's 1. And cos pi over 2, that's 0. So f's first derivative evaluated at pi is 1. Let's do another derivative. Second derivative. It should give us our final term. Third and final term. First three terms, right? So differentiate sine x over 2. We get half cos x over 2. And then the next term we're going to use the product rule. So differentiate x over 2 or half x. We get half. And we put back the cos x over 2. And then we know how our product rule is. Now we're going to keep the x over 2, but differentiate cos is minus. So it's actually minus x over 2. And differentiate cos, well, minus sign, we have minus, the minus is already accounted for. To differentiate that, so it's cos x over 2, so it's half, actually minus half, sine x over 2. And then we evaluate at pi. We evaluate a second derivative at pi. So we end up with now, what we end up with now. So cos pi, so this will be 0, cos 90. Cos pi over 2, that's 0. Again, that's 0. So sine pi over 2, that's sine pi over 2. What's sine pi over 2? 1. So that's negative x over 4. So that's negative x over 4. And we're replacing x with pi. So that's negative pi over 4, negative a quarter pi. So this simply means that the Taylor series, so therefore x, the Taylor series x sine x over 2 at pi is equal to f of pi, which we found to be pi, plus x minus pi times f prime pi. Now f prime pi was 1, so it's just x minus times x minus pi. And the next term is a negative term. Is it? Next term is a negative term. Negative. And this is what? X minus pi all squared times, so negative. So x minus pi all squared times the second derivative evaluated at pi, which is negative pi over 4. Alright, so this should be can I put the pi out here? Over 4. Over 4 times 2 factorial, which is 4, so it should be over 8. So those will be the first 3 non-zero terms.